All right, let's dive right in. Today we're looking at something that sounds like it's straight out of science fiction: dynamically doped liquid superconductors. It's a pretty wild story, folks. It kicks off with a claim that sounds an awful lot like alchemy, but it ends with a technology that could literally change the world as we know it. So, let's get into it.
So let me just start with a question that, honestly, feels like it should be asked in a medieval lab, not a modern one. Can simple sound waves, just sound, actually turn one element into a completely different one? I mean, that idea alone pretty much challenges everything we think we know about physics.
Because, believe it or not, that's the core claim we're digging into today. There was this really controversial experiment that suggested if you blast liquid mercury with ultrasound, you could actually create gold, along with a bunch of other stuff. So, what on earth is going on here?
To figure that out, we have to start with the experiment itself, because the results were, and I'm putting this mildly, completely and utterly shocking.
Okay, so back in 2017, a research team reported something that just sounds, well, impossible. They took regular liquid mercury, hit it with some seriously high-powered ultrasound for just 3 minutes, and watched as part of it just turned into solid grains. And here's the really weird part. This happened at 260 degrees Celsius. That's hundreds of degrees above Mercury's normal freezing point. It just shouldn't happen. But the real bombshell dropped when they actually analyzed those solid grains. They found a whole zoo of new elements that just weren't there to begin with. We're talking everything from superlight lithium to heavy hitters like gold and even radioactive thorium. It looked for all the world like random modern-day alchemy. But was it truly random?
For a few years, this whole thing was just a weird footnote, a scientific anomaly. That is, until an independent researcher, Nicholas Fenning, decided to take a much closer look at that list of elements, and what he found was a stunning, hidden pattern in all that chaos.
And this number right here, this is the key, the absolute key to this entire puzzle. When Fenning analyzed the properties of every single one of those new elements, he found a perfect correlation, 100%.
100% correlation to what, you ask? Superconductivity. Yeah, you heard me right. Every single product element, from the titanium to the tin all the way to the gold, is part of this exclusive club of materials that can become superconductors. Fenning gave this a name, the quantum selection rule. It was this massive blinking sign that whatever was happening, it was anything but random.
And this is the point, you see. This pattern changes the whole story. It goes from being this bizarre, no way that happened kind of anomaly to a genuine scientific mystery that needs a solution. It's a puzzle that suggests some new kind of physics was at play, a hidden mechanism that for some reason loves to create superconductors.
So, to explain this puzzle, Fenning came up with a whole new theory. He calls it the Runaway Galvanic Boost, and it is a totally radical way of thinking about how matter can be fundamentally reorganized. Okay, so the theory starts with this wild idea called the supercoherent quantum state. The thinking is that the intense pressure waves from the ultrasound don't just shake the mercury atoms around. Oh no. They actually force the messy, chaotic liquid into a super-organized, synchronized structure. It's like a mosh pit at a concert suddenly snapping into a perfectly synchronized marching band.
And this chart here just nails the difference. In a normal liquid, atoms are all over the place, right? And electrical resistance is high. But in this theoretical supercoherent state, the atoms get organized, they're in sync. And the biggest, most important consequence of that, the electrical resistance should absolutely plummet. Now that's a great theory, but is there any actual proof that sound can do this to a liquid metal?
Amazingly, yeah, there is. Back in 2015, a totally separate, peer-reviewed study did almost exactly this. They took a liquid metal alloy, blasted it with ultrasound, and measured its electrical properties. And what did they find? I'm quoting here, a substantial and lasting drop in electrical resistivity.
And that, my friends, is the smoking gun. It is the exact electronic signature Fenning's theory predicted. It's real-world experimental proof that, yes, ultrasound can push a liquid metal into that low-resistance, highly ordered state, the perfect setup for these crazy transformations to kick off. So, if the theory actually has some legs, how do you harness it? Well, Fenning didn't just stop with the theory. He went ahead and actually designed a machine that could control and sustain this entire process.
He calls it the tri-field activation chamber, and it's basically built on a dance between three different forces. You've got the acoustic field, that's the ultrasound to get the whole thing started and condition the mercury. Then you've got an electric field for propulsion to get the liquid moving. And finally, a magnetic field to control that movement, basically turning the electrical input into a nice, stable spin.
Now here's where it gets really elegant. The way these fields work together creates something called a dynamo feedback loop. You know that horrible high-pitched squeal you get when a microphone is too close to a speaker? That's audio feedback, right? The sound is feeding back on itself and amplifying. Well, this is kind of the same idea, but instead of making a terrible noise, it's used to stabilize a quantum state. It's brilliant.
So let's break it down into 4 simple steps. Step 1. The external fields get the mercury spinning. Step 2. As that conductive liquid spins through the magnetic field, it generates its own electricity, just like a little power plant dynamo. Step 3. This new, self-generated current acts like a constant kick, locking the mercury into that stable, super-coherent state. And finally, Step 4. The system becomes self-sustaining. The spin makes the current, and the current stabilizes the state needed for the reaction to keep on going.
Okay, this is all fascinating stuff, right? But let's take a big step back and ask the most important question of all. What if it actually works? What would our world even look like if we had on-demand, room-temperature superconductors?
First up, energy. It would mean a power grid with zero loss. No more wasted energy during transmission. That would directly lead to cheaper utility bills for absolutely everyone. And, maybe most importantly, we could create massive, perfectly efficient batteries to store renewable energy, solving the biggest problem with solar and wind power once and for all.
In our personal tech, just imagine charging your phone or your car in a matter of seconds. Your device batteries could last for weeks because almost no energy is being wasted as heat. And the computing power in your pocket could rival today's supercomputers, unlocking true, real-time AI for everybody.
In thinking bigger, on a global scale, we're talking super-efficient maglev trains becoming the norm. Medical tech, like MRI scanners, could become smaller, cheaper, and way more powerful. And let's not forget where this all started. This could become a new way to create valuable materials on demand, without ever having to dig them out of the ground. So we're left with this absolutely tantalizing possibility. A story that starts with a seemingly impossible experiment, uncovers a hidden pattern, and then lays out a radical new theory for the future. The only question left is, what is this? Is it just a brilliant but unproven dream? Or is this the first real blueprint for a completely transformed world? The answer? Well, the answer could redefine everything.